So this is basically a schematic illustration of this lab device. If you look at this picture here, so we have soil specimen. And you notice that the soil specimen is submerged in water. So you have this water table here. So this test is conducted in fully saturated condition. So your soil specimen is fully saturated during this entire process. So it's submerged in water, and you have this porous stone just to keep the soil samples in place. And this device is called odometer or consolidometer. And there are two main objectives for this consolidation test, as I mentioned. The first one is to simulate that compression of soil, basically deformation load response. And more importantly, to obtain these moduli and indices you need for consolidation calculation. And specifically, so you're going to get these indices and moduli in CC, CS, C sub V, and sigma C prime. Okay. So I'm going to explain all these indices in a little bit, but these are the four main quantities we need from consolidation test. So two compressibility moduli, coefficient of consolidation CV, and preconsolidation pressure sigma C prime. Okay. So these are the modular indices we need for consolidation calculation. Okay, and then for this 1D lab test, okay. So during the this 1D consolidation test, you apply load, this load P here, incrementally. So you apply incrementally. And in this process, okay, so you apply one increment of load, say 500 PSI. And then for this load increment, you allow the specimen to consolidate and come to equilibrium. So that means you need to allow sufficient time for that sample to reach equilibrium. And you also allow the excess pore pressure to dissipate. So the excess pore pressure is approximately equal to 0 when that equilibrium state is reached. Okay. And this means your total stress is the same as your effective stress. So after the excess pore pressure is dissipated. Okay. So you allow the water to dissipate, the pore pressure to dissipate. So you reach an equilibrium state where total and effective stress is the same. Okay. Right. And then I put a note here. So typically, if you look at the standard, for each load increment, you want to hold it for about 24 hours so that all the pore pressure can be dissipated. In our lab, you'll see the holding time is shorter than this. So we're not aiming for like 100% primary consolidation, but we're getting close to that just to approximate that. This will speed up our test. And then the next load increment typically doubles the previous one. And the data, as I mentioned, so deformation versus stress. And this stress is applied load over area. So you get deformation versus stress or deformation versus load. And of course you have time as well. Okay. So that's the data you get from 1D consolidation. That's the raw data, deformation, and then applied load and the corresponding time. Okay. So if you look at this, this is just a deformation versus time data from a 1D consolidation test. And on this graph, there are actually three clear stages. The first one, this is the, we call initial compression. This is due to the elastic deformation. In this stage, as I mentioned, either elastic deformation and or the initial gap between soil specimen and your loading plate. So that's initial compression. In the second stage here, that's the focus, primary consolidation. And last one is secondary consolidation. So this is basically what the raw data might look like. So you have these three stages. So deformation versus time. Right. So with this data, we're not actually going to directly use deformation time plot for this modulus. We're going to accept the coefficient of consolidation. We're going to actually convert the results to void ratio versus pressure plot. Okay. So void ratio. And this pressure is basically that if vertical effective stress. So I use pressure here, but it's actually referring to the applied vertical effective stress, the vertical stress. And there are number of steps you need to take to convert this deformation data to void ratio data, and then plot it with your vertical effective stress. Okay. So I listed 5 steps here. I'm going to flip through those slides. You can take a look at them. And also in the lab, you'll be given a handout that actually covers these 5 steps as well. Okay. And for these 5 steps, so basically you convert the deformation to void ratio. Okay. And so this red plot here, so this is actually from the phase diagram. So if you recall phase diagram in chapter 3, so we're separating the solid and void phase. And the void ratio is the ratio of void over, the volume of void of volume of solid. Okay, so that's how you get a void ratio. It's to figure out how much voids are in the soil. And you can calculate void ratio. So I'm going to flip through these steps here. You can take a look after lecture, or again, this will be in the handout, lab handout. Okay. But the result of this process, as I mentioned, you convert your lab data to this void ratio in the vertical axis, and effective pressure here, sigma prime, that's your effective vertical stress in log scale in the horizontal axis. So that's the data you're going to get, you want from the 1D consolidation test. Okay. So from this plot, so the next topic I want to cover, so this is 1D consolidation test. So you want this void ratio and pressure. So I want to cover is what information you're going to get from this curve here. Okay. So this leads to the next topic, preconsolidation pressure, and also a few modulus here. So the first one on the right-hand side is that same plot, void ratio versus effective stress or effective pressure. Okay. So on this figure here, I included an unloading circle. So initially you have this initial loading. This is initial loading. Okay. In this initial loading stage, you can see the steep, the slope is a steeper slope. Okay. So it's called CFG. Okay. Just focus on this later stage of this slope. So you have a steeper slope. This is the initial loading. And then CD here. Okay. So at some point, we're doing an unloading. And this is also called rebounding. And then after that, D and C again, this is reloading. And after C, the material goes back to the initial loading. So this is very typical this is what you typically observe in 1D consolidation test of clay. So that's loading, unloading behavior. And so what I want to point out on this graph is if you look at the slope of this curve, you can clearly observe two different slopes. So the initial AB and also CD part. So you have a flat slope. And then for the initial loading, the slope is much steeper. Okay. So this is because I put a point here, clay has a memory of stress history. Okay. So basically depending on where you are in your loading history, the clay will behave differently. So here comes this concept of preconsolidation pressure. Okay. So a soil in the field has subjected to a certain maximum effective past pressure in its geological history, and we call that maximum effective past pressure preconsolidation pressure, sigma C prime. Okay. So this preconsolidation pressure, so depending on the relationship between your current effective stress and this sigma C prime, clay is going to follow different path when you load it. Okay. So on this one here, this CD and DC portion here. So if you're loading clay and the current effective stress, any point on this portion of the curve is smaller than its maximum in the past, okay, somewhere close to C. In this case, clay is going to follow that flat curve, so flat slope, okay, because clay knows its current stress is smaller than its maximum in the past. However, on the initial loading portion, the current effective stress is the maximum. And in that case, clay is going to follow this steeper curve. Okay. So this is different from sand and gravel. So clay, you need to know its preconsolidation pressure in the consolidation calculation. So let's dive into this curve a bit more here. So on this slide, I'm showing an idealized void ratio log sigma prime curve. Okay, so this is basically the same curve, but I'm just taking the linear average of these two portions, basically. And again, this is that unloading, reloading, okay. And this is the initial loading. So that turning point, so from unloading, reloading curve portion to that initial loading, that turning point is actually the preconsolidation pressure sigma C prime. And of course, this is an idealized curve. So you have a very clear turning point. So that's your preconsolidation pressure. But in the actual test, let me flip back one slide. So in the actual test, this turning point is not that obvious. So you need some procedure to determine that. Okay. So we'll talk about that in just a minute. And then the slope of this loading portion, so this initial loading, is also called virgin compression portion. And this is what we call CC. And this is called compression index. Okay. So that's this CC. And then the slope of the unloading, rebounding, and reloading portion, we call CS. In some books use, some textbooks use CR as well. So this is called recompression. Or swell index. Okay. So that's these two slopes. Okay. So C and CS. So this is the idealized E log sigma prime curve And to determine this pre-consolidation pressure, so as I mentioned, in this idealized curve, this point of changing slope is pretty obvious. Okay? But in reality, your curve would most likely look like this one. Okay? So there's no like sharp turning point. And to determine that sigma C prime consolidation pressure, the most commonly used procedure is this Casagrandi's procedure. Okay? And this is a graphic procedure to determine sigma C prime from your E log sigma prime curve. And this is actually a pretty simple process, just 4 or 5 steps here. And I put a recorded video online, so you can take a look at. It's only a minute and a half, so it's a pretty simple process. You can take a look at, and that gives you basically for this E log P curve, the pre-consolidation pressure. Okay. So that's what you want to get from this curve. Okay. So that's something you can watch after today's lecture. Again, just a very short, very simple video on this sigma C prime, how to determine sigma C prime. Okay. So that's Casagrandi's procedure. And then a closely related concept to this pre-consolidation pressure. So as I mentioned, pre-consolidation pressure is the maximum past effective stress. And depending on the relationship between your current and the maximum past, you can classify clay into normally consolidated and over-consolidated clay. So the first one. So these NC clays are basically for soils that have present effective stress. Let's call this sigma prime. So this is present. Okay. So if the sigma prime, the present effective stress is the maximum, so it equals to sigma C prime. So the soil is called, with the clays is called the NC or normally consolidated clay. So that's NC clay. In the second case, it's called over-consolidated clay. That's where your effective stress, your present effective stress sigma prime is smaller than its maximum in the past. So smaller than the pre-consolidation pressure. So that's NC and OC clays. And we can define over-consolidation ratio using sigma prime and sigma C prime, so OCR. So you can define this as a ratio of these two stresses. Okay. Sigma C prime over sigma prime. Okay. So for NC clay, sigma C prime, sigma prime is the same, so OCR is 1. And this is NC clay. So clay is normally consolidated. And then for OCR greater than 1, you have OC clay. Right. So these are the two types of clays based on the relationship between sigma prime and sigma C prime. Okay. So NC clay, sigma C prime, sigma prime is the same. In OC clay, sigma C prime is larger than sigma prime. Okay. So the significance of these two types of clays when it comes to consolidation, if you're loading a normally consolidated clay, the stress is going to follow this initial loading portion. And so it's going to follow the steeper slope, so the initial loading, which has a steeper slope. Okay. So it's going to follow this initial loading portion that has a steeper slope. And this means that for a given effective stress change, for a given load increment, you're going to expect more void ratio change. And void ratio change directly relates to settlements. So you're going to experience more settlement. For OC clay, so stress will follow the reloading. So this one has a flat slope. And the implication of this is for same load increment, there's less void ratio change, and hence there's less settlement. Okay. And so the other one exception is unloading. So if you're unloading a clay, even if it's a normally consolidated clay, so unloading is going to follow this portion. So unloading is going to follow that this same portion. Okay. So it doesn't matter if it's NCOC. If you unload the material clay, it's going to follow the flat slope. So therefore, in general, NC clays are weaker and more compressible. Because when you load NC clay, it's going to follow this steeper slope. Same loading, it incurs more settlements. So it's more compressible than OC clay. And that is the reason why you preload a site. So remember that example, the example soil layer I gave at the beginning. Okay. This is a very common practice. So before you construct anything on top, you preload the soil, the clay layer with some sandy fill on top, so to preload. Okay. So this means you're increasing the effective stress in this clay layer. So you're moving clay to basically to this side. Okay. So you're increasing the effective stress in the softer clay layer and hold it for a while, okay, to let the excess pore pressure dissipate, to let the primary consolidation complete. And then when you want to construct something on top, you say when you want to build a building on top, you remove the sandy fill. So clay is going to basically unloading. It's going to go through this unloading path. And when you put your new structure on top, so say you build 3-story, 5-story building on top, clay is going to follow this reloading portion. And that is basically less compressible. So you have much less settlement expected compared to the case where you don't preload the site. That's why you're preloading the site to basically over-consolidate the clay layer and to make it stronger and less compressible. So that's NC and OC clay. I think that's a good point to stop here today. In the next lecture, I'm going to finish this introduction portion, and we're going to focus on that settlement calculation. So basically using what we learned from the 1D consolidation test for field settlement calculation.